We're counting down 8 of Atlas's most puzzling anomalies, the kind that leave even top space agencies short on explanations. This interstellar visitor shows suspicious alignments, odd optical behavior, and chemistry that refuses to fit the usual Comet playbook. Each entry stretches what we think we know about objects that drift in from beyond the sun's reach. The ranking moves from attention-grabbing coincidences to deeper physical mysteries, sparking everything from chatter about missing photos to energetic theories about hidden technology. Some claims rest on solid observations, others on bold speculation, but all of them raise the same question: which anomaly is the hardest to explain? Let's begin with number 8. Coming in at number 8 is its proximity to the famous WOW signal. As it approached, its path passed within about 9 degrees of the coordinates tied to that 1-minute radio burst recorded in 1977 by the Big Ear telescope in Ohio. The original beam was less than a degree wide and pointed to a specific spot in Sagittarius, while Atlas's course fell just outside that narrow window, but in the same broad area of sky. At first glance, that closeness can sound eerie. 9 degrees is under 1% of the whole sky, like finding 2 people in the same city across an entire country. In astronomical terms, though, that separation is still wide enough to rule out a physical link. No repeat of the WOW burst has ever been heard, and the span of time and distance between the two events makes a direct connection extremely unlikely. Even so, the coincidence is irresistible, showing up in podcasts, message boards, and a few early papers. With only 3 interstellar visitors on record, any directional overlap stands out. Statistically, patterns like this appear by chance when there are thousands of possible alignments to notice, a classic case of post hoc selection bias. We spot matches after the outcome is known. It's an appealing detail, but it doesn't diagnose anything on its own, leaving the mystery more atmospheric than evidential. The 7th anomaly is Atlas's razor-flat orbital tilt. Instead of diving in steeply from above or below the solar system's plane the way most interstellar objects do, Atlas schemes just over 3 degrees above the ecliptic. In orbital geometry, that's almost perfectly flat. By contrast, Oumuamua crossed at a dramatic angle and Borisov took a sharply tilted path, while Atlas hugs the same thin disk the planets use, like a car merging smoothly into a highway lane. Basic probability says a random interstellar arrival within 5 degrees of the ecliptic is rare, while under 1%, so a measured inclination around 3 degrees is eye-catching. Some scientists point to observational bias, since Earth-based surveys are more sensitive to objects moving near the ecliptic band. Even when that bias is considered, the approach still feels unusually flat. With so few interstellar objects to compare, it's hard to tell whether this is luck, selection effect, or a hint at deeper dynamics in how such bodies are ejected and steered through space. At number 6 is the polarization that refuses to flip. Polarization reveals how dust grains scatter light, which in turn exposes their size, shape, and composition. For Atlas, early reports triggered debate because multiple telescopes measured polarization that stayed strongly negative at viewing angles where most comets switched to positive. Around a 30-degree Sun-Comet Earth angle, values dipped below -2%, extreme for any comet, especially one from another star. Typically, comets show negative polarization only at tiny phase angles near zero, then cross to positive near 20 to 25 degrees. Atlas seemed to buck that rule, keeping negative values well past the usual crossover. Teams checked calibration, weather, and stray light, but the pattern held across different nights, instruments, and filters. The most straightforward explanation is unusual dust, perhaps large, fluffy aggregates or material richer in carbon and complex organics than average, more like delicate cosmic snowflakes than ordinary sand. That kind of structure would naturally scatter light in a way that preserves negative polarization longer than expected. 5th is the chemistry that won't fit the standard model. Spectroscopy delivered strong neutral nickel lines near 3,414 angstroms, while iron, which normally tracks nickel 1-for-1, remained faint and hard to detect. In familiar comets, nickel and iron rise and fall together as dust rich in both metals escapes the nucleus. In Atlas, nickel stood out clearly while iron clung to the noise, a split not seen in typical comet spectra. Analysts rechecked calibration and atmospheric effects, but the pattern stayed stable across nights and instruments. The common comet bands C2 and Cn appeared but were subdued, hinting at a mix comparatively richer in metals and poorer in the usual volatile organics. If follow-up space-based observations confirm this, ATLAS would mark a sharp break from the norm. Iron-poor, metal-rich chemistry is uncommon in the outer solar system and almost unknown among interstellar visitors. Composition like this could also help explain the optical oddities, because different metal ratios change how sunlight filters through the coma, altering color and polarization the way unusual spices shift a recipe's flavor. Fourth is the sun-facing jet. The most striking images show a faint fan that seems to flow toward the sun, flipping the textbook picture that always points tails away from sunlight. Time series data from major observatories caught a forward-leaning plume that looked like venting from the leading edge rather than the trailing side. Analysts tracked its orientation over multiple nights, accounting for rotation and changing illumination, and the fan held its sunward lean even as the coma brightened and the main tail formed in the usual anti-sun direction. Sometimes perspective tricks can flip a tail's apparent direction when our line of sight grazes the comet's orbital plane, producing so-called anti-tails. In this case, the geometry kept supporting a true forward fan over a range of phase angles, resisting the standard projection explanation. There are rare precedents where vents near the subsolar point or buried pockets of volatile ices produce unusual jets, but a clean forward fan at this distance is still uncommon, keeping this feature high on the anomaly list. The third is size. Photometric models that combine coma brightness with the faint signal from the nucleus point to a diameter around 5 kilometers, more than 3 times wider than either of the earlier interstellar objects. With standard assumptions about reflectivity, that implies a mass upward of 30+ billion tons. By any measure, ATLAS is a heavyweight, not just compared with Oumuamua and Borisov, but within the small family of bodies suspected to arrive from other stars. Population models say large objects should be rare and small fragments common. If that's true, surveys should have logged many more pebbles and boulders before turning up a giant. Instead, the first 2 were small, and the third suddenly massive, like spotting a whale before seeing any minnows. That lopsided sequence challenges expectations and keeps the debate alive over how representative these finds really are. At number 2 is the trajectory that seems almost too clean. On October 3, 2025, ATLAS passed Mars at about 28 million kilometers, a near miss in cosmic terms, and a very low probability event for a random interstellar traveler. The flat orbit then set up a chain of encounters, a pass near Venus, and later a distant brush with Jupiter. Each flyby is rare on its own. The full sequence is rarer still, like winning 3 lotteries in a row. Then comes the twist. Despite active jets venting material, the comet's path barely deviated from predictions. Many comets show clear non-gravitational pushes as outgassing acts like weak thrusters. Borisov drifted noticeably, and Hale-Bopp shifted by more than 10 kilometers per day at peak. ATLAS stayed close to a ruler-straight arc for months, implying that any jet forces were tiny compared with its inertia. The simplest way to square strong activity with minimal deviation is mass. A very heavy nucleus shrugs off its own thrust the way a freight train ignores a gust. A few theorists suggest more exotic ideas, from unknown physics to some form of guidance. But most working astronomers still favor a natural explanation while admitting the statistics are uncomfortable. The final anomaly sits in ATLAS's chameleon glow, rapid, repeating color shifts in the coma that don't track the usual chemistry curves for distance and heating. Across its approach, observers noted phases where the coma trended red and dust-rich, then swung to brief green emissions typical of dicarbon or CN, and later showed blue-leaning tones associated with stronger CO/CO2 activity, changes that arrived faster and with sharper transitions than standard sublimation models predict at similar phase angles. In familiar comets, color evolution broadly follows heliocentric distance and illumination, with dust reddening dominant far out and gas bands strengthening smoothly as sunlight drives out gassing. ATLAS, by contrast, appears to toggle regimes, as if venting pockets of compositionally distinct ices from different layers or fractures that switch on and off as the nucleus rotates. The simplest natural reading is patchy stratification. Buried reservoirs rich in CO/CO2 and complex organics erupt as specific vents hit sunlight, briefly overpowering the baseline dust signal before quenching, which would also dovetail with its unusual polarization and forward-facing jet. Yet the cadence and amplitude of the color swings remain awkward for a uniformly active surface, and the timing near key geometries invites alternative explanations ranging from transient plume optics to larger grain dust injections that scatter light differently. Whatever the driver, the Comet's quick change palette adds another data point to Atlas's pattern, behavior that mimics known comet physics and outline, but with timing and intensity that keep pushing the edges of expectation. Taken together, these 7 anomalies explain why Atlas doesn't feel like an ordinary comet. The near-perfect ecliptic approach, stubborn negative polarization, nickel-rich and iron-poor chemistry, and a sunward jet all break familiar patterns. What truly sets it apart, though, is the blend of a large, heavy nucleus and a sequence of low-probability planetary passes paired with minimal non-gravitational drift. Each feature is rare by itself. Stacked together, they remind us how little we know about what wanders between the stars. Atlas isn't just another icy rock. It's a signal that the solar system remains open to surprises, and that the universe still holds more secrets than we expect.